Hello everyone, you're welcome to my YouTube channel. My name is Ridwan Ibrahim, and first of all I want to apologize for being off on my YouTube channel. It's been quite a while now that I've ever posted a tutorial here, and many of my viewers have reached out to me who are genuinely worried about me. They've reached out and asked what is going on, if I'm fine or something. Well, I'm actually doing fine. I've just been quite busy with academics, but then I hope that I'm fully back. So in this new course that I'm launching, it's a different dimension from the conventional tutorials that I've been making, but it's all in the same aspect of civil engineering and structural engineering. So in this new episode of courses that I'll be having here, it's titled AI in Civil Engineering, simply artificial intelligence in civil engineering. So in this, we'll be finding the middle ground, the integration of AI in civil engineering. So we will look at several analyses that we do in civil engineering. It could be risk analysis, it could be structural health monitoring, it could be a lot of things. It could be some infrastructure or the mobility part of civil engineering. So there are so many aspects of civil engineering that we could apply artificial intelligence. And when I say artificial intelligence, I actually mean machine learning, deep learning. You could go up to different aspects like NLP and all of that. So the first question we will be asking ourselves is that, okay, well, why is this actually needed? Because sometimes I see a lot of people trying to embed AI in some aspect that does not actually require AI, so by embedding AI in that, it makes it more difficult and make it more complex. So do we actually need AI in civil engineering? I think this is quite a very old question. Everybody has an answer to, but I would still like to answer it. All right. So initially, we all have experimental analysis. We do experimental analysis. For example, if you want to determine the compressive strength of a concrete, you just get a specimen, say a 20 by 20 concrete, and then you take it to the lab and then you crush it. So you take the ratio of the crushing force over the surface area of the specimen, the test cube, and then you get the compressive strength of the concrete. That is an experimental analysis. But then we have a numerical analysis as well, where you can simply do something similar numerically, maybe with abacus or with, I don't think ANSYS is quite, ANSYS is also an FE analysis engine. But then you can use different numerical analysis that is based on FEA, right, to do similar analysis. So that is a form of, it's also a form of analysis which is quite different from experimental analysis. And then now we have the data-driven analysis. Data-driven analysis in here is a kind of machine learning based analysis whereby we take a data and then we learn from the data. It could be past data, it could be a temporal data that is happening immediately, but we learn from the data and then we make decisions based on the data. So for example, this course that we will be having will be a data-driven analysis, whereby we'll be doing what we have in this first picture. We will be predicting the strength of a concrete. All right. So when you have a concrete inside, instead of taking it to the lab, you can just do a data-driven analysis on that concrete, and then you get your compressive strength instead of actually taking it to the lab. Then we have a physics-guided analysis. Physics-guided analysis is more or less like the combination of numerical analysis and data-driven analysis. So in this case, you are not having the data. You are not feeding only the data. You are not doing a statistical analysis only on the data. You are also imbibing some PDEs so that you can put that in the loss and help the model learn some physics so that it's not purely data-driven. So in this case, we are not actually replacing the experimental analysis, but we are just providing a separate method that could be maybe less expensive, because if you want to go to the lab, you have to pay and do all of that. But if you have your model built in already, you can simply feed in your new data into it and, predict your strength with a very good accuracy. All right. But it doesn't replace experimental analysis. It's just to, commemorate it. All right, so what are the core concepts of what we'll be expecting to see in this course? Well, we will be working on data engineering. We'll be doing some classical machine learning, and then we'll be doing some deep learning. The good part of this is that I will be using just one data set to do all of this. So we will not be moving, we will not be having like different problems and different solutions kind of. We will only have one problem, but then we'll be solving it with different kind of solution. It's just like when you have a beam and then you're trying to calculate it with slope deflection, you want to calculate it with moment distribution method. You're using different kind of method, but it's still the same problem. So in this case, it will also be the same problem. We will just be exploring different methods, right? And you might be wondering why I have this data engineering first before we even go into the classical machine learning. Yeah, because when I see a lot of videos online, or maybe on Coursera or Udemy, the tutors, they just go directly into the machine learning. They don't bother teaching you the data engineering part. But most of the time, when you have the data is not clean. The data is rough. The data is not usable. If you build a machine learning model on the data that is bad, then your model will be bad. So you need a good data to be able to produce a good model. So in this, we'll first of all see how you can, when you get a rough data, how can you make it a good data? How do you know exactly what to feed into your model? How do you know what to build your model upon? So we will be doing that, and then we go to machine learning and the deep learning. All right, so under the data engineering, what do you expect to see? Well, we will do some data cleaning. So we will look for missing values, duplicates, we will detect outliers, we will check the distributions. We will do some exploratory analysis whereby we want to know what is the correlation of this data, what is the kurtosis, what is the skewness and all of that. We will also work more on visualization because you need to visualize what you're seeing. We will see the feature relationship, we will see multicollinearity. We will do some information theory as well. Granger causality, actually causality is not an information theory, it's more or less like an uncertainty analysis, but then I decided to just put it under information theory. And then we will do some feature engineering. So feature engineering is simply when you're trying to create a new parameter. Say for example, what you need is not given, but you can get what you need from what is given. I don't know if that makes sense. So let's say for example, you want to calculate the pressure on the wall. You have a wall, you want to calculate the wind pressure on that wall, but you don't have the data for the wind pressure. What you have is wind velocity, but you know that there is a relationship between wind pressure and wind velocity. Wind pressure is simply 1/2 multiplied by the density of air multiplied by the square of the velocity. So you could just do that small calculation and get pressure. So what you just did right there is called feature engineering. You get a new feature from a feature you have already. Okay, so we will do that and see how that can help us in our analysis. And then we go to the machine learning and the deep learning models. So basically we will work with 6 models. I don't know why I have 0, 1 here. It should be 0, 6. So we will work with linear regression. So that's like the most basic model for any regression problem, because this problem is not a classification problem, it's a regression problem. So we will be working with linear regression. And then we'll do some regularization. So we'll try to also work with ridge regression and lasso regression. Then we will see how we can improve that with polynomial regression. So if you see the way these are arranged, they are kind of like arranged from simple to like maybe more difficult, kind of like that. So in polynomial regression, we are trying to replace the straight line with a curve. And then in decision trees, so decision tree is a kind of like dynamic model. You can use it for classification and for regression. In this case, we'll be using it for regression. And then for random forest, well, random forest is like an ensemble of decision trees. So decision tree is like one tree. But then random forest is like when you have a lot of decision trees. So you are making them to work together. And then when we are done with all of these machine learning models, we would try to see if we can solve that with artificial neural network, which is just a neural network, and that's the deep learning part of it. So we'll try to play with it. We'll play with the activation functions. We will do some back propagation, feed forward, and all of that. So these are the requirements and the results that we are expecting to get from this. So the scope of the problem, basically, as I said, we are trying to predict the compressive strength of concrete. And then the data set, it has 8 features and 1 target. So what does 8 features mean? Well, I will explain that better when we begin the project. Then the prerequisites, what you need to know before you start this course. Well, you need to have a basic understanding of Python structure, because to be honest, I will not be teaching you Python. I will try as much as possible to make it a very simple code. It will not be Pythonic. It will just be regular Python code. But you need to understand that. But the Python part is just, coding part of it. The actual stuff is more like mathematical and all of that. And then you need some analytical skill. You need to be able to analyze this is what is going on, And then the dedication, the personal hour that you need to dedicate per week. It's flexible. You can come here, you can just watch one episode today, go back and come back maybe tomorrow. It's fine. So, and then the uniqueness, why this course is actually very unique from the other courses you'll be seeing online, is basically in here, we are blending engineering with machine learning integration. We are not just, if you go online, possibly you just see a random data set. It's telling you about stock prices. It's telling you about maybe a prediction of house prices. It's telling you about, all these things are good, but they are not applied directly into your field. So in this case, we are embedding it directly into our field. So that's the uniqueness. And another thing is that we'll be doing a step-by-step intuition. I will not build the code and be explaining the code to you. We will be building it together, all right? And then we'll be using a real-world data set, all right? So what I expect that you will have after this course is that you'll be able to build a full machine learning pipeline. You should be able to compare machine learning and, deep learning, ANN. You should be able to interpret a model. When you have a model, you should be able to explain the model, like explainable AI. So we might try to do Sharp or Lime eventually. And then you should also be able to deploy a trained model. You should be able to deploy it with Pico or wherever so that you can use it, in your day-to-day activity. So this is just the introductory part of it. I wanted to keep it short, but apparently it's quite long. But then see you in the actual episode where we start the first part of the project. Thank you.